So that is what we're going to do. Now, let's just go ahead and go to click 1. We know that we only need the y velocity, correct? So if we look at our calculator, you'll see that all we need, I'm in the wrong folder. Go back to Hooke's law, sorry. I go to Hooke's law, Hooke's calculator, you'll see that all we need is y for the first compression, second compression, and third compression. So let's go ahead and go back to Microsoft Excel. Let's go back into our folder, pull the data in, and then do a wee bit analysis, wee bit. So we're in Hooke's law now. So let me go ahead and go to click 1. And I think we need y here. So I'm just going to copy that. We don't necessarily need to convert and edit anything. We're just copying our data from it. I thought that you used to have to, but come to find out, don't need it at all. Just going to paste that. Going to check my data out. All right, very good. Initial velocity is 2.9. I'm going to go ahead and put in my 3.1 here. I know that's what I have for kinematic theory, the initial velocity using kinematic theory, and I'm just going to put this in a percentage. So we're getting like 8.19% here. Let's do number 2. Yep, I'm just going to copy that. Go back into Hooke's calculator. We're in number 2, paste. So we're coming out with 3.6. I think my kinematic theory came out to be something like 3.5. And you'll see the percent difference is still coming up as a non-percentage. So let me just select the formatting, and the formatting is coming out to be 3.79. That's really good. And then we'll do our last one here. It's number 3. So I'll try to open up, make sure I'm getting the right one. Copy, go back. Then I'm just going to go ahead and paste this in. So you'll see that I have 5.4 here. I'm not sure. I think this was like 5.7, 5.6, 5.6. And let's select percentage again. Okay, this is pretty good. We were firing it out with kinematic equations. This is where you're going to get these kinematic theory initial velocity. Remember, you're going to get it from experiment number 5 and your midterms, your middle term experiments. So when you were finding the initial velocities. And now let's look at Hooke's law. Look at this. The velocities were coming over, and we are coming out with a spring constant that is 108, and then 94, and then 114. I was expecting these just to be straight across the board the same. But this is showing you that it is not the same. I wonder if anybody can tell me why, anybody can figure out why that is the case. Think about it. Google it. Wikipedia. Okay, it is that way because the spring is traversing a large, it's translating a large amount, okay? Translational motion is large, whereas Hooke's law was about very small elasticity. So even though I have this plastic piece here, it's like, can I squeeze it? Yes, you can. And under that limit, the law will remain the same. The constant will remain the same. So we're just able to apply it to springs. Let's look at the velocity versus the height. So you'll see that I have velocity down here, but actually it should be over here. I'll change that, but compression distance should be at the bottom. Our compression length should be at the bottom. And then initial velocity should be over here. So you'll see as we compress more and more, we get of course, we get a greater and greater velocity. We can most likely make draw some conclusions about this. So I could always bring up chart and layout, and then they can give me an equation of the line. And this will let me know, well, how well, it'll give me an opportunity to predict what's going to happen if I keep taking points in between this spring. So that's enough of that. And then let's look at the compression distance versus the spring constant. So you'll see that it's really doing something different here, okay? It would be nice to see at different lengths what would happen. And that's pretty much the end of the lab. Make sure you guys submit this. Make sure you have your data sets in here, and know that there's no video and there's no snapshot. Okay, au revoir.